In this video, I'll go over the quiz questions on crystalline solids. So first, which of the following two ions has a larger ionic radius? Always pick the negative ion, so chlorine minus here. The reason is the size of an ion or atom depends on the effective nuclear charge. And what's the effective nuclear charge? That's the number of protons in the nucleus minus the electron shielding. Minus the electron shielding. So if you have more electrons than neutral, well, there's going to be more shielding. If you have fewer electrons than neutral, well, there's going to be less electron shielding. So when you have more electron shielding, like this case, the effective nuclear charge is smaller, and therefore the valence electrons in chlorine minus feel less attraction. Therefore, the structure is more loose than neutral atoms or positive ions. So anyway, when you see this kind of questions, always the negative ions have a larger ionic radius than the positive ions. The neutral atoms are in the middle. Question 2. Click this link and calculate arc sine 0.25. So we need to find an angle, theta, and sine theta should be 0.25. How do we do this? Well, you can use your calculator, but you can also just use this Wolfram Alpha website. I highly encourage you to use this Wolfram Alpha or Google to do your calculations. It's convenient, and it sometimes show you steps, so you understand how this is being solved. Okay, now in this case, arc sine is just the opposite of the sine function. The result is here 0.05 or 2.866 degree. And our question is the arc sine of 0.25. So I'm going to change the number and click this equal sign again. Let's see what's the number. So in radian, it's 0.25268. In degrees, it's 14.48. So let's see. Well, over here, degrees. Question 3, an X-ray beam with a wavelength of 123 picometer is incident on atomic crystal. And then we have the angles, we have this n value. Well, how do we compute the separation between layers of atoms? So there's an equation. It's 2 times d times sine theta equals n times lambda. All right, so what's 2 times d 2 times sine theta? Well, that's when you have 2 light waves being reflected by the first layer of this atomic crystal versus the second layer. They travel a different length. And what's the difference? That's 2d sine theta. And if we are trying to observe the maximum reflection, that means constructive interference. Therefore, they should differ by either lambda or 2 lambda or 3 lambda, so that their crests coincide and their troughs coincide. That gives you the maximum constructive interference. In this case, let's say just they differ by just 1 lambda, assuming n equals 1. So lambda is 2 times d times sine theta. Sine 30 degrees happens to be 1/2 times 2 times 103. The result should be 103 picometer. Okay, now an X-ray, again X-ray with, now this time 60 picometer wavelengths. And we have the separation between the layers of atomic crystal 120, and then we're going to calculate the incident angles with the maximum refraction. So this is constructive interference, and because again the equation is 2d sine theta equals n lambda. So n can be 1, n can be 2. So 2 times d times sine theta can be 1 lambda or 2 lambda or 3 lambda, etc. So we're going to use the two smallest angles. We're going to look at just 1 lambda and 2 lambdas. So 1 lambda over 2d. So 1 lambda over 2d. That's going to be just 60 over 240. It's going to be 0.25. So we're talking about arc sine 0.25. I think we got this number before. And then 2 lambda is 120 picometers over 2d over 240. That's 0.5. So we know arc sine of 0.5 is 30 degrees. So it's going to be 14.5 and 30 degrees. Let's see. 3 out of 3. Quiz 12.2. The number of atoms in a simple or primitive cubic unit cell is 1. So you have 8 corners. On each corner, you have 1/8 of the atom. The number of atoms in a body-centered cubic unit cell, it's similar to the simple cubic unit cell. The difference is there's one extra atom, the whole atom at the center. So 1 plus 1 is going to be 2. Number of atoms in the face-centered cubic unit cell, again, on the corners, there are 8 corners. You have 8 times 1/8 atoms. That's only 1 atom. And then look at the 6 faces. You have actually 6 of them, but you can only count 1/2 for each face. So that's 3. 3 plus 1, that's 4. The edge length of a simple cubic unit cell is approximately or exactly how many times the radius of the atom. So you just need to look at the picture of a simple or primitive cubic unit cell. You realize that the edge length is 2 times the radius. Similar question, but we're talking about body-centered cubic unit cell. So this time, if you look at the body diagonal of the cell, it's the square root of 3 times the edge length. And that's equivalent to 4 times atomic radius. So the result should be 4 divided by the square root of 3. The square root of 3 is 1.732. So I think this is the answer. 4 divided by 1.7 something is 2.3. The edge length of a face-centered cubic cell. Again, you need to look at the picture. You realize the face diagonal is the square root of 2 times the edge length, or 4 times the atomic radius. So your answer should be 4 divided by square root of 2. The result is 2 times the square root of 2. Square root of 2 is 1.414. Therefore, the result is 2.828. Sodium has a body-centered cubic unit cell. Its atomic radius is 190 picometer. Calculate the edge length. So it's just 190 meters times 2.309. It's going to be this. Done. Again, it's 190 cubic meters times 4. You'll get the body diagonal, all right, between 2 opposite corners of the cube. That's the so-called body diagonal. So 190 times 4, that's 760. And then that's the square root of 3 times the edge length. So you have to use 760 divided by square root of 3. So 760 divided by 1.732. You get 4 point something. All right. It's over here. Oh, by the way, 1 picometer is 10 to the power of negative 12 meters. And also, it's equivalent to 10 to the power of negative 10 centimeters. So this 1 picometer is 10 to the power of negative 10 centimeters. 190 picometers is 1.9 times 10 to the power of negative 8 centimeters. All right, so I changed the units from picometer to centimeter, so pay attention. Picometer is 10 to the power of negative 12 meters. Centimeters are 10 to the power of negative 2 meters. Sodium has a body-centered cubic unit cell, and we have the radius. And then what's the volume of such a unit cell? We do have the edge length, so the volume of such a unit cell is just the edge length to the power of 3. So 4.4 to the power of 3. 4 to the power of 3 is 64. 5 to the power of 3 is 125. So the number is going to be, I think, a little smaller than 100. And then times 10 to the power of negative 24. So let's find that number. Okay. So this is close. This one is roughly 85 times 10 to the power of negative 24. Again, this number to the power of 3 is 80 something. And this is going to be 10 to the power of negative 24. Put them together, it's going to be this. By the way, you can use Wolfram Alpha or Google to do the calculations. Calculate the mass of sodium. Okay, it's just the atomic mass of sodium, that's 23 AMU, but you have 2 sodium atoms, so 46 AMU. And 46 AMU is 46 grams per mole. So you need to have 46 divided by the Avogadro constant. And then 46 divided by 6. It's this. Alright. The density of sodium is, well, in this case, this is the mass of 1 cubic unit cell. And that's the volume of 1 cubic unit cell. So this number divided by this number in cubic centimeter. I think the result is going to be roughly 0.9. So because this number is smaller than this number by a small amount, maybe roughly 0.9. This two cancel. So 0.9 gram per cubic centimeter. So here. So look, the density of sodium is lower than the density of water. So if you threw sodium in water, it's going to float on the surface of water. That's interesting. Submit quiz. Let's see, 5 out of 5. So we move on. Which two of the following solids are molecular solids? So we're looking for solids that consist of molecules, and they are attracted by intermolecular forces such as dipole-dipole interaction. So dry ice or dispersion. Between CO2 and CO2, there's dispersion. Over here, between water and water, there's dipole-dipole interaction. So these two are made of CO2 molecules and water molecules. And between those molecules, there's no real chemical bond. There's just dispersion. And over here, dipole-dipole interaction. So what about table salt? Okay, that's actually ionic compound. Over here, this is metallic atomic. Which two of the following solids are ionic solids? You need positive ions, negative ions, so this two. Which two of the following solids are metallic? So look for metals, magnesium, copper, we're good. How about this two? They are ionic compounds. You have positive ion, negative ion, positive ion, negative ion. Which of the following molecule solid has the highest melt point? Okay, highest melting point. Look for the greatest attraction between neighboring molecules. So it's going to be dipole-dipole here between water molecules. Over here, dispersion, dipole-dipole. Those are all small molecules. So roughly the same dispersion. So if they have roughly the same dispersion and fairly small dispersion because they're small molecular size, let's focus on the dipole-dipole interaction. These two do not really have dipole-dipole interaction. So between ice and ammonia, ice has the stronger attraction between water molecules for two reasons. So in ice, each water molecule can form 4 hydrogen bonds. So in 1 mole ice, we have 2 moles of hydrogen bonds. Again, each bond is shared by 2 water molecules. Over here, each ammonia can form 2 hydrogen bonds. One via the lone pair on the nitrogen, the other one from one of the 3 hydrogen atoms. So on average, in 1 mole ammonia, you have 1 mole hydrogen bonds. So if you just look at the numbers, the ice wins. And also, actually, the OH hydrogen bond is stronger than the hydrogen-nitrogen hydrogen bonds because the electronegativity of oxygen is higher than that of nitrogen. So I'm going to pick ice. Which of the following molecular solids has the lowest melting point? So look for something without a dipole moment with the smallest dispersion. So let's look at this. Dipole, dipole, dipole. This one, no dipole, nitrogen, no dipole, okay? Which of the following molecular solids has the highest melting point? Okay, they look similar. They all have a OH, OH, OH. Now just pick the one with the greatest dispersion. Very long carbon chain. There's going to be a lot of dispersion between two neighboring this kind of molecules. Okay, I need to count the number of carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decanol. Okay, DECANOL. All right. So in organic chemistry, you'll learn this. Methane, propane, butane, and then pentane, hexane. Oh, and by the way, if you have OH, you just replace A and E for alkane to alcohol. So replace A and E with OL. All right. So pentanol, hexanol, septanol, octanol, etc. Which of the following molecular solids has the highest melting point? Again, look for the dipole first and then compare the dispersion. So this one, ethane and the propane, they do not have this OH functional groups. They cannot form hydrogen bonds. So I'm going to pick either this one or this one. But now look at this molecule. It contains two hydroxyl functional groups. It's going to form twice the number of hydrogen bonds of this one. So I'm going to pick this. Submit quiz. All right, 5 out of 5. We move on over here. Which of the following atomic solids has the highest melting point? We look for the atomic solids in which atoms form real chemical bonds. So over here, there's chemical bonds between oxygen atoms and silicon atoms. All right. Between sodium atoms, there's metallic bonds, but metallic bonds are weaker than the bonds between silicon and oxygen. These two are just noble gas atoms. Lowest melting point, so look for noble gas atoms over here. But I want to talk about this. Diamond has the highest melting point for sure. Okay. Which of the following solids has the highest melting point? Okay. Ionic, metallic. So pick ionic. 1, 2, 3. And then look for the charges. Which ionic compounds give you the highest charges? These two. Calcium oxide, magnesium oxide. So there's a tie. Okay, remember, when you compute the electrostatic attraction, it's going to be Q1 times Q2 over the distance. So between these two is plus 2 times minus 2 over the distance. Plus 1 times negative 1 over the distance. Plus 2 times negative 2 over the distance. So we're going to go with the greater charges. So either calcium oxide or magnesium oxide. And then what about the distance? Magnesium 2 plus has a smaller ionic radius than calcium 2 plus. So between magnesium oxide, between these two ions, the distance is smaller, therefore greater attraction, highest melting point. So I think magnesium oxide has a really high melting point, maybe 2000 degrees Celsius. Which of the following solids has the lowest melting point? Ionic. They have really high melting points, so sodium, metallic. Metallic bonds are weaker, or even much weaker than ionic bonds. To compute the lattice energy of sodium chloride or the enthalpy of formation, we also need, okay, this is a little bit complicated. So how do we compute the lattice energy of sodium chloride? All right, lattice energy. That's the energy released when you have sodium plus and the chlorine minus react and form this table salt. And what about the enthalpy of formation? Enthalpy of formation, that means we start from the elements. We start from sodium solid and chlorine gas. Those are the elements of sodium and chlorine. So there's a gap there. So what we need is, we do need to breach the gap. We need to go from this sodium solid to sodium atom, and from sodium atom to sodium plus. So we need the ionization energy of sodium. We need the enthalpy of formation of sodium atoms. Also, we need to go from chlorine to gas to chlorine minus chloride. So from chlorine to gas to chlorine atom, that's the enthalpy of formation of chlorine atom. And if we go from chlorine atom to chlorine minus, that's electron affinity. This will give you some qualitative understanding about the Hess's law, actually. This is based on the fact that enthalpy is a state function. Metals such as gold, silver, and sodium are brittle due to the strong repulsion between neighboring metallic atoms. No, there's no strong repulsion between metallic atoms, so false. All right. Ionic compounds are brittle. Are brittle because when you knock ionic compounds over here, it's possible to knock off layers of ions. Okay, by just, even one layer, one atomic layer, you will have positive ions really close to positive ions, negative ions really close to negative ions. This whole huge repulsion will break up the salt. So I'm gonna just choose true, submit quiz. All right, 5 out of 5. We're done with